Welcome to a highly strategic, totally insider look into the examiner's mind. Today, we're tackling a consistently misunderstood, totally foundational topic in the Cambridge Computer Science Syllabus 9618, and that is clock speed. Now look, whether you built your foundational knowledge in earlier syllabuses like 0417, 0478, 0983, 0984, 2210, or even 9713, the step up to 9618 is massive. And honestly, most students prepare for this completely wrong. They memorize the fetch-execute cycle, they memorize the definition of clock speed, and then they just stop there. They think that's enough. But by the end of this explainer, you are going to possess a complete toolkit that transforms your raw textbook technical knowledge into an undeniable, high-scoring exam strategy. We're going to bridge that gap between knowing the facts and actually getting the marks. So let's dive right in. Okay, what's really, truly interesting here is this direct quote pulled straight from the principal examiner reports. It says, candidates referencing cross-topic connections achieve significantly higher marks. I really want you to let that sink in for a second. The conceptual framework for factors affecting computer performance, like clock speed, isn't just an isolated island of knowledge. You can't just silo it away in your brain. The theoretical architecture rests on precise definitions, yes, absolutely, but more importantly, it rests on causal relationships and integration with completely different syllabus areas. Memorizing isolated, standalone facts about clock speed just isn't going to cut it anymore. The examiners are explicitly telling us, right here in black and white, that they are looking for connected, applied knowledge. They want to see systematic analysis. They want evidence-based reasoning. If your exam strategy is just rote memorization and regurgitating the textbook, you are literally leaving an enormous amount of marks on the table, and we are going to fix that today. To brilliantly illustrate exactly what I mean, let's look at a real-world scenario. We see this all the time. Let's contrast two very common yet deeply, deeply flawed student approaches. Okay, on the left we have Alex. Now, Alex has studied hard, really hard. When confronted with a question on clock speed, Alex just overloads the answer with raw computer science facts, writing down absolutely everything they know about gigahertz, cores, caches, you name it. But Alex provides zero analysis of the specific scenario given in the prompt. It's just a giant information dump. Then, on the right, we have Sam. Sam is panicking about the time limit, watching that clock tick down. Sam rushes through the calculations, entirely misses the specific command word requirements, words like evaluate or justify, and completely ignores the overarching context of the question. So what happens? Both students fail to achieve top marks. Not because they don't know computer science. They actually know it quite well. But because they lack a precise strategic methodology in the exam room. They aren't answering the question the examiner actually asked. So here is our playbook for this explainer. We're going to break this down logically. First, we'll decode the examiner mindset. Second, we'll establish a rock-solid technical methodology. Third, we are mastering critical evaluation. Fourth, I'm going to reveal the top 3 examiner warnings. And finally, we'll synthesize it all into your ultimate winning exam strategy. Let's move right into our first pillar. Section 1, the examiner mindset. Specifically, we need to talk about understanding cognitive domains. Here is the secret. The examiner isn't just asking, what is clock speed? Anyone can answer that. They want to see high-level cognitive domains in action, like application and analysis. And this brings us to a concept that literally separates the A-star students from the rest of the pack. It's called transferable understanding. What does that mean? Well, you might be perfectly comfortable calculating performance metrics for a standard desktop PC, right? But what if the exam presents a proprietary embedded system in, say, an automated factory sensor network? The physics of the clock speed remain exactly the same, but the context has completely shifted. Mastering this adaptation, your ability to apply established foundational principles to completely unfamiliar, highly specific situations is your absolutely critical first step to mastering this exam. Moving on to Section 2, Systematic Technical Methodology. We are going to build a procedural framework. But before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's break down this procedural framework. As I mentioned earlier, the step up to the advanced 9618 syllabus requires a rigorous shift in how you process data. The examiner expects a standardized sequence. You can't just wing it. Step 1, identify the key elements. What is the specific hardware architecture being described in the prompt? Step 2, apply relevant principles. For example, how does an increase in clock speed dynamically interact with a change in cache size? Step 3, execute analysis with clear working. This means actually extracting data from the system specs provided and mathematically proving your point. Step 4, verify the results to ensure your calculations make logical, real-world sense. And Step 5, present in an appropriate format. Now, what do I mean by that? I mean using proven frameworks like PEAL. That stands for point, evidence, explanation, link. You don't just dump numbers on the page. You structure a logical, easy-to-follow path. You make your point, you back it up with evidence from the prompt, you explain how that evidence supports your point, and you link it back to the core question. You construct it so the examiner can effortlessly follow your reasoning from start to finish. Now, the crucial point we really need to focus on is what we call the method mark strategy. This is an absolute cheat code for Cambridge exams. Marks are awarded for the execution of the process and your clear working, not just the final calculation. Let me paint a picture for you. If you attempt a complex clock speed conversion or a multi-step performance calculation in your head and you just write down the wrong final answer, you get 0 marks, period. But if you write down every single step of your systematic processing, even if you make a silly minor arithmetic error at the very end because you're stressed, the examiner will still award you method marks. Demonstrating your analytical process on the page is a guaranteed way to secure marks and insulate yourself against simple pressure-induced mistakes. Show your work. Always. Let's shift gears to Section 3, Mastering Critical Evaluation. We're going to look at how to evaluate algorithms in the context of hardware. You see, practical application questions don't just ask you to build something or calculate a number. They require you to test, to evaluate, and to justify. Evaluating algorithm quality requires a highly specific set of metrics. You must analyze time complexity. Think big O notation. How does the execution time scale as the data input grows exponentially? You also must analyze space complexity. A processor with a blisteringly fast clock speed might still completely bottleneck if the algorithm's space complexity causes constant cache misses. You also need to actively identify edge cases and ultimately determine the precise performance impact. The examiner desperately wants to see that you understand a fundamental truth. Raw hardware clock speed is entirely dependent on the quality of the software running on it. A fast clock speed can't save a terrible algorithm. Now let's look at how to structure a truly top-tier comparative analysis. When a question asks you to compare 2 different processor setups, identifying similarities is only half the battle. Sure, you might note that both have matching underlying architectures. That's fine. But the real marks, the high-grade marks, are in identifying the differences. And listen closely. You cannot just list them. You must use specific comparative connectives, words like whereas, conversely, or in contrast. And every single comparison must be backed by solid evidence extracted directly from the prompt. You aren't just stating that System A is faster. You are proving it using comparative terminology and drawing a concrete conclusion about its relative importance to the specific task they gave you. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @theaceexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's do a quick interactive workshop challenge to test your critical evaluation skills. Imagine an exam answer that reads exactly like this. System B has a 4.0 GHz processor compared to System A's 3.0 GHz processor. Therefore, System B will run the database search faster. I'll give you a second to really think about it. What is the missing analytical flaw there? Well, the flaw is that it completely ignores the PEAL framework and the command words. It makes a point, sure, but it provides absolutely no deep explanation or link back to the specific context. Does the database search rely more on parallel processing with multiple cores, or is it a sequential process? Is the whole system actually bottlenecked by secondary storage read speeds rather than the CPU clock speed at all? A top student points out these exact nuances, showing the examiner they understand the holistic, interconnected nature of computer performance. Okay, moving into Section 4, the top 3 examiner wordings. These are direct, high-stakes insights from the people actually grading your papers. Pay very close attention, because these next points are the exact pitfalls that consistently bleed marks from otherwise perfectly well-prepared students year after year. Here are the top 3 exam mistakes pulled directly from the examiner reports. Number 1, students completely forget to check overflow and edge cases. When calculating performance or converting binary representations related to processing speed, an overflow error changes absolutely everything. Number 2, failing to check boundary conditions. When an algorithm scales up, what happens at the absolute physical limits of the processor's capability? Students rarely, if ever, evaluate this. Number 3, and honestly, this is the most fatal of them all, providing answers that are not specific to the context given in the question. If the question is about a real-time hospital life support system, your evaluation of clock speed must center entirely on reliability and immediate, guaranteed execution. You can't just talk about generic processing speed. Context is absolutely everything. And this brings us to a massive, critical warning from the examiners themselves. I want you to treat this like an urgent intervention. The examiner report literally states, students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. I cannot stress this enough. Abandoning your scratch pad, trying to do complex hex to binary conversions in your head, or hiding your calculations is the absolute easiest way to fail. The examiner cannot read your mind, they can only grade what is physically on the paper. You have to build a visual map of your reasoning right there on the page for them to follow. Finally, Section 5, the winning exam strategy. Let's pull everything we've talked about into one final system. Let's synthesize all of these tactics into one cohesive answering system designed for maximum mark potential. This is what we call the ultimate deconstruct, solve, evaluate framework. Step 1, identify given information. Literally highlight the command words on the paper. Step 2, break the complex problem into smaller, logical steps. Step 3, solve systematically using the structured knowledge we've discussed today. Step 4, check for reasonableness. This is huge. If your calculation suggests a processor will take 400 years to execute a basic loop, you have missed a boundary condition or made a massive arithmetic error. Step 5, make justified recommendations. This is where you bring it all home. You don't just state the final result, you justify why that result actually matters in the highly specific context of the exam prompt. So this brilliantly illustrates your final blueprint for conquering the 9618 examination. Deconstruct the question, extract the data, select your framework like Peel, execute notation, and present terminology clearly. Applying this exact rigorous sequence to past paper questions until it becomes absolute muscle memory is exactly what elevates a student to top-tier marks. And listen, the proof is in the results. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. As we wrap up our analysis in this explainer today, I want to leave you with a direct question. When you look at your past papers, what is your absolute biggest hurdle when dealing with clock speed and evaluating computer performance? Take this blueprint we just built, pull up a past paper right now, and start applying it today. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.